Hey all, we'll get started in a few seconds. Please trickle in. Could we get a note taker? I'm staring into people's eyes. Oh, amazing. Thank you, Mallory. Could someone shut the doors? Thank you. Thanks. All right. Welcome all to the final day of IETF 117. We are the Privacy Enhancements and Assessments Research Group. I'm Shivan, and we have Sarah joining remotely, and Chris as well, maybe. All right. This is the note well. I'm sure you've seen it by now, but please do read it carefully. And just a reminder that this session is being recorded, and you are expected to follow IETF processes and policies. Just some meeting tips. Please make sure that you are signed into the session using Meet Echo, and you are using Meet Echo to join the mic line, just so that we are fair with folks attending remotely. And if you haven't used the Meet Echo Lite agent thing, please scan the blue sheets. I think they're over there. If you wouldn't mind just sending across the blue sheets. QR code. Yep. Thank you. And thanks, Mallory, for taking minutes. Cool. Yeah, this is our agenda. And we have some time at the beginning for draft statuses. And we have our first RFCs. We have 2 new RFCs that PEARG published. And Fernando, I believe, will be talking about them later on today. And we have 1 draft in RFC Editor Q, the survey of worldwide censorship techniques. That should also be, thankfully, progressing soon after many, many years. And then we have the guidelines for performing safe measurement on the internet draft. Mallory, did you want to give a quick update on that one?
Mallory Nodal, CDT. Yes. So that a few weeks ago, I sent a revision for this draft on safe internet measurement. And I consider it the first real full version. Previously, we had the table of contents. We had quite a lot of text there, but there were still some unfinished sections that I've brought a few times to this group because we did a sort of table of contents revision, and I'm quite satisfied with the structure of the document. But now I'm also satisfied that it's full and it's filled in. It actually provides guidance on all the things it intends to. So if you could please review it, I think it would be getting quite close to last call just because it's not meant to be a terribly long document. And it does have text on all of the things that we've intended to cover and care about. I'm going to be proactive in reaching out to the folks who have provenanced this draft, the Tor Safety Board, that it's based on their guidelines for when folks go to Tor and ask to measure the Tor network. They review a checklist, and this is essentially the checklist but adapted for the IETF environment. And so I'll be reaching out to the folks that sit on that board for their reviews. And if others have ideas for other groups aside from PEARG that might want to review this, I'm thinking of MapRG. Anyway, I'm willing to do the work to send it around to get some reviews. But if you all could also review it, I would appreciate that. And then we can move it forward.
Yeah, thanks. Maybe a PPM as well would be a good venue.
Really obvious. Yeah, good idea. And if folks think of something later, just send me an email or a Zulip message and I can action that for next week.
Thank you. All right. Yeah, we can move on to our first presentation by Reza. Reza, if you wouldn't mind sharing your screen again, and I can grant you access. I'm clicking the grant screen. It's not doing anything. Oh, oops. Thanks.
All right. Hello, everyone. I'm Reza. I'm a professor at National University.
Reza, your audio is very choppy. It was perfectly fine until. Yeah. Can you? Maybe I'll just. Can you try again? I'll just revoke video and audio and just try requesting access again.
Can you hear me now? Hello?
Yeah. It looks
Am I
like it's better
audible?
now. Yeah, Reza, is it? I think. Can you request access to just share preloaded slides, and we can try to do that instead of sending the screen? And your slide deck should be on there.
I don't find it there.
Just maybe try reloading meeting materials. I don't know if that's a per user view. It should be the privacy in language models. Yeah, Reza, maybe I'll just share the slides for you and you can say next slide and we can go that way.
But the screen sharing is working, right?
It was just really choppy, like we couldn't hear you at all.
I see. Okay. All right. Yes. So let's continue this way.
Oh. Okay. Can you try this, Reza? I think you should have control now.
Okay. Sure. Yes. It seems that I can go to the next slide.
Perfect.
Yes. Okay. Very good. So hello, everyone. So I'm very excited about talking about this very interesting and important topic, the data privacy in language models. And before we dive into the details of the relation between language models and privacy, we need to understand what privacy means in general in the context of machine learning. And I want to separate two different notions. One is the direct privacy risks of using machine learning. Similar to any other type of computation, when sensitive data is used in a system, we want to make sure that only authorized users have access to that. And we want to prevent, in other words, the direct privacy risks. And this is where confidentiality comes into the picture. But something that I want to focus on today, and is the more subtle risk, is the indirect privacy risk in machine learning, where sensitive data is used for training a model, and now the model itself or the outputs of the model might leak information about the data, right? So if the data is sensitive and the model is leaking information about the data, then somehow unintentionally we are allowing unauthorized access to the data, right? So this is the concern that we have with respect to machine learning algorithms in general. So for language models, I don't want to go into the complex details of how they operate, but in a nutshell, what they want to do is to mimic the way that we used to talk based on the data that the algorithms that are available to the algorithms up to a certain point in time. And what they do is that they try to, in a sequential manner, complete sentences based on the samples that they had seen in their training set. So the data sometimes is non-sensitive, but in very many cases, the data on which language models are being trained today and definitely will be trained on in the future are very sensitive. There could be medical data, which are very sensitive and personal. There could be enterprise data, which are very sensitive. And also it could be all the conversations between users in different platforms, which contains very personal information. So the concern is that the language models that are so powerful to learn the patterns of how to place different pieces of text together based on their training data, they also memorize some pieces of that text that could be extracted later on and reveal sensitive information about the users who contributed data to the training set. So indirectly, unintentionally leak information about the training data. And this is real. Language models do leak information about their training data. And it has been shown repeatedly by different researchers, including my team, that large language models, the vulnerability of large language models could be exploited by inference attacks. An adversary who has just access to the model would be able to identify which data points were used to train the model. So for example, for the sensitive data sets such as medical notes, which are used to fine-tune language models and create, let's say, clinical language models, we have shown that it's very easy to extract that sensitive information. Also, for some other language models, researchers have shown that you can extract some sensitive information like phone numbers and social security numbers if they are used in the training set. This has nothing to do with the language, as we all agree, but this is the side effect of using these models. So if the data is personal and sensitive in the context of large models, models are personal data. If we are concerned about sharing the data because of the sensitive information which is embedded in them, we also need to be concerned about sharing the models. But it's very hard to protect this leakage, and later on we will talk about that. But first, before we talk about how to mitigate the risks of training large language models on personal and sensitive data, we need to have a way to audit data privacy in these cases. We need to be able to measure how much the leakage is with respect to the data that was used during the training. We need a metric. And way that I would explain how to measure leakage in machine learning, I would like to use a game, a hypothetical scenario. Imagine that there is one world in which we are training a model on some training set, and there is a parallel world in which uh, new data set, a new data record, for example, a new document, or all the text produced by a particular user is added to that training set, and we train a model. So there are these two parallel worlds. In one world, my data is used in the training set, and in the other world, it is not used, and everything else is the same. Now, in this hypothetical setting, I place an adversary randomly in one of these worlds, and I ask if he would be able to detect in which world he is in. And so in one half probability is in this world or the other world. And the question is whether the adversary can distinguish between these two. The only thing which is different between the two is the presence or absence of my data. The adversary observes the model or predictions from the model or samples from the model and needs to guess that. So we all admit that if the adversary wins this game, if this hypothetical adversary wins the game and manages to find information and signals in the output of the models that enables him to differentiate between these two settings, the algorithm is leaking information about my data. The algorithm enables the adversary to single out me based on the data that I contributed to the training set. In other words,
Reza, your audio is getting choppy again. Can you try requesting audio again?
right.
And let's keep the video off just to preserve
Okay.
some bandwidth. Yeah, that sounds better, I think. Can you try again?
Yes.
Okay, yeah,
Am I audible?
Yes.
Yeah. So the success rate of the adversary in these membership inference attacks would measure the leakage of models about their training data, right? So I hope the setting is clear. To just visualize this, you can imagine that different users have provided their data. A subset of these are universe. And then what the adversary does is that for any data point in the universe, runs a transformation function to map them into a space that gives the probability that, let's say, these a data point could have been member of the training set of a model. So the ones that are on the left are the ones that the adversary thinks with higher chance were part of the training set, and the ones on the right are just random data points in the population. The adversary can place partitioning or threshold to determine which data points are member or non-member. This is the identification attack, right? So any individual, given the model, would either fall into the left side of this line or the right side, and the adversary would say, well, the ones that are on the left are the members. These are the ones that adversary identifies as members of the training set. It's going to make...
Sorry, we had a question, I think. Would you like to take the question right now, or would you like to wait until the end?
Yeah, I would continue the presentation and then leave some time at the end for the questions.
Okay.
Or in the middle of the talk, basically, there's a part that I can pause a little bit.
Okay.
So then, this is basically the attack, right? This is basically the identification attack. If you are unlucky and the adversary would correctly detect you as member, then information about you is leaked through the model parameters or predictions. And or coverage plays a very important role in the metric. Also, the error plays a very important role in the metric. This is the way that we can show this. That, let's say, imagine that in this spectrum, where every individual gets a score, the adversary could be very conservative and say, well, I want to identify one single data point that for sure was part of the training set. Then the threshold would be all the way to the left. Or the adversary might want to say, well, I want to identify everyone that was in the training set, even though I'm going to falsely believe some other non-members are part of the training data, right? So this would result in a profile, which is the dotted line, for example, shown here in the red area, and for, let's say, the language models. But depending on where the profile is, where the error versus the accuracy of the attack falls, we can...
Sorry, Reza, would you mind requesting audio access again? That seems to work, but it was getting choppy again. We can't hear you. Are you speaking? Reza, can you try sending audio again? Yeah.
Hello?
Hi, yes, we can hear you again.
Okay, yeah, sorry about this. So I was saying that based on the performance of this analysis, we can partition different algorithms into low risk, medium risk, and high risk. That reflects to what extent is the risk of singling out individuals versus how much each individual is blended into the population. This is a very standard way of measuring the privacy risk in machine learning algorithms. It has been reflected in many guidelines and for AI. And mitigating this risk of membership inference attacks, which reflect exactly how much the model leaks about this training data, is part of the requirements that are the privacy risk, we can see that as the amount of information that we have about an author increases, the chance that we can identify whether his speech was part of the training set increases. And very few sentences are enough to identify that some text was part of the training data. The tool and similar tools would also enable identifying vulnerable training data. Ironically, in this case, the vulnerable training data are data which are talking about sensitive information. And so I would like to wrap up the part about quantifying privacy risk is that we need to measure how much presence of certain information in the training data would be leaked through the parameters or predictions of the model. And that needs to be part of any privacy auditing and comparing.
Yeah, Reza, we can't hear you again. I'm just going to do the same thing, revoke audio, and just request audio again. Yeah, you have audio access now. Can you try speaking?
All right.
Yeah, we can hear you. Thanks.
So if there is any question about this first part about auditing, I think there was a question. This is a good time to ask.
Yeah, Jonathan, did you still want to ask your question?
Jonathan Hoyden, Cloudflare. This question actually came up in the Zulip. Is the presupposition that the attacker already knows all the data in the model and wants to know if it's there or not? Because I don't really care if the attacker can do that if it already knows all the data. I don't want it to have the data in the first place.
Okay, it looks like Reza's offline. Oh.
All right. So you were talking about the assumption of whether the adversary knows all the data in the training set.
Yeah, the slide 21 or whatever it was.
Sorry, I didn't hear I just heard the first part of your, I didn't hear the question, yeah.
If we assume that the attacker already has the data, then I don't care what he can do. He's already won before the game started.
So no, the adversary does not know the training data. He only knows that's the problem that he has to solve, right? He does not know whether your data is in the training set or not. Right?
Right. He doesn't know whether it's in the training set or not. But if he already knows the data, then I don't care.
Yes. So this is a yeah. So no. This is the private information. The secret is whether it's there or not. This is not a real adversary. This is a hypothetical adversary to just measure the leakage of the algorithm. It's not that there is a real adversary out there that has the data and wants to know whether you used it or not. That's a separate scenario. Like, for example, you want to know whether some company used your data during training or not. That's a separate question. Here's a hypothetical scenario that these two worlds we just simulate to just measure how much information about presence of any point in the training set will leak all the way through to the predictions of the model. And we just test it this way.
But it feels like I don't understand why that's measuring the right thing, right? You could instead measure how many numbers, how many sixes are in the data set, right? That's a measure, but it doesn't measure the right thing. Why is knowing whether the data was trained on the right thing for measuring privacy leakage?
So imagine this. Imagine that there is a training set and an algorithm is running on that training set and train a model, right? Which will become available publicly. Now you want to know whether you should participate and add your data to the training set or not. So your concern is whether by adding my data to the training set, do I make enough changes, distinguishable changes to the model such that the adversary that can reverse engineer it and point to my data? If the model with your data, without your data are indistinguishable from each other, such that no adversary can differentiate between them, then it means your data was not leaked, right? So it's safe. You can contribute your data.
Okay, so this is whether I decide to join some data set or not, rather than given that all these large language models exist, is my data everywhere?
Yeah, it's just, to me, that's the same question, right? So you can use it as a decision making for whether to participate or not. You can also use it as a way to just say, if we add it, how much it would leak, right? Because if it leaks, then I'm not going to participate. Because the idea is this: if I'm running an algorithm to train a model, the expectation is that it should extract the general patterns out of the data set, right? It should not extract something that only applies to my data. My social security number, that particular sequence of numbers, is not something that the model should remember or should produce. But any random number is okay, right? You should be able to learn fake social security numbers. That's what I want the language model to learn, but not to reproduce my number, right?
Makes sense. Thank you.
So if you want to now say, okay, this was a way to quantify the risk, but one thing that we want to do is this: we say, well, we need to preserve privacy as well, right? So this was a way to quantify the risk. We showed that actually language models leak a lot of information using this technique. We need to preserve it. But first, we need to know, okay, what does it mean to preserve it, right? In the general context.
We have one more question. Chris, did you still want to ask your question? Or?
Sure, go ahead. Yes.
Is this vulnerable to guessed data? So for example, you can imagine a data set that was trained on medical data, right? And so if somebody wants to know if I have a particular medical condition, can they guess? Does the training set contain Chris Lemons treated for acne or whatever? Is it vulnerable to guesses like that?
So let me rephrase your question and ask it this way. If I want to check whether it would reveal that sensitive piece of my data, is this way of evaluating and auditing privacy risk relevant, right? Because I'm just looking at whether my data is there or not there. Can you detect it? And you're saying, well, okay, maybe he can say to some extent that my data is there or not, but what I'm concerned about is whether the disease is X or Y, right? If the disease, X being X or Y, is very atypical, right? Such that your record is like so different than any other patient's record, then detecting whether your record is there or not is mostly due to that something that distinguishes your record from the others, right? But okay, this is answer number one. And answer two is that we can develop an auditing technique to just answer your question. Instead of saying whether your record is in there or is not there, I'm saying whether it's there with this property or whether it's there with that property. I can still run the same game. And then that way I can measure the uncertainty of adversary in distinguishing these two within the same framework. Yeah.
Tommy?
Tommy Polly Apple. Yeah, I think I was thinking along the same lines as Chris here, of essentially saying, to Jonathan's question, like, how is this actually a problem?
Mhm.
If you could use this as like a way to like brute force some existence proof of like, okay, Jonathan's SSN is this, and I just figure out which one has the higher confidence on it, then I have a pretty good likelihood of extracting that data. So that seems like a legit privacy concern.
Exactly. So you can use this membership inference attacks in terms of, instead of asking it in a binary form, you can ask it with multiple questions and also quantify that risk, if that is a specific risk that you want to measure. But something is that that is very important is that in this question that you asked, you highlighted a particular sensitive piece of information which might not be known or be identifiable in all cases. So what we want is that in a generic way, without specifying a particular attack, we want to measure leakage. But is that all? What does it mean to preserve privacy, given that there is all this leakage? I want to broaden the discussion a little bit and say that privacy in the realm of languages is super difficult to define. Language is a medium for communication. It reflects all our life. Okay, so it's as complex as the language itself. So the privacy in language is as complex as the concept of privacy in real life. So if you can define what exactly privacy is, come up with specific rules for privacy in the real life, then you would be able to extend it to language as well. But that's a very hard problem to begin with. Privacy is also very contextual. Something could be sensitive in one context if it's shared and not sensitive in the other context. As human, what we do is that we choose whether or not to disclose or conceal information depending on the context. You tell me something, I sense whether that is sensitive or not, and I decide whether I share it or not to the other party. But this is the question is whether I can sense the context. This is very hard. Sometimes the context is just beyond the text itself. Language models just look at the text. First of all, it's very hard, if not impossible, to detect whether something is sensitive or not, except for very specific cases of sensitive data. And in many cases, because the context is beyond the text, it becomes impossible to know whether a certain thing is sensitive or not. So for protecting privacy, first we need to identify what is sensitive, right?
Reza, just a time check for maybe around 5 more minutes.
Sure, yeah. And then the private information can take many different forms. One of you just asked about, a disease, the type of disease and so on, but it's way beyond that, right? So there are so many different ways that you can reflect something which is sensitive in your daily communications with your colleagues, family, and others, and friends. And there is no simple way to come up with a rule with that. Private information also has no boundaries. Alice might say something and which might not be reflected in Alice's data, but it could be reflected in Bob's data. So user 1 information might reveal information about user 2. Also, we cannot say if something is repeated many times is public. In many cases, for example, in organizations, there are lots of secrets that everybody talks about, but it's private. Language models, we know that they would just learn more, something which is repeated more. So what are the existing privacy preserving methods? Scrubbing, removing secrets from text. You define what a secret is, remove it before training. Differential privacy, train a model that makes the auditing technique that we discussed before fail, such that without your data, the algorithm results in indistinguishable models. Or use public data, crawl the internet to gather all the available text. But these are all based on some assumptions. Scrubbing assumes that you can come up with a rule for removing every secret. Differential privacy assumes that the secret is entirely in one's user data. So everything sensitive about me is in my record. And using public data assumes that publicly available data is public intended. If I put something somewhere or post something on Twitter and so on and so forth, I meant it to be used forever by everyone. But these assumptions are incorrect or inaccurate. I mentioned that it's very hard to come up with a rule for identifying secrets. The data, the sensitive information about one user could be in many users' data. And what I share publicly, I share with some intention in mind, which is not being used by everyone. So this is a very challenging situation we are in. We are using language models, and the existing techniques are not perfect. So what are the paths forward? This is a very hard problem, so there's no solution right away. But one thing that we can definitely agree on to do in a systematic way is the following. So we should make use of publicly intended data. There are lawsuits right now against some companies that crawl the internet to train models. So instead, it should be data which is from the first day is generated for public use. We can use private personalization. So for a user who is going to use a language model, maybe he should be the only one that has access to the model if his data is used for training that, or for the enterprise as well. So personalizing models for every user or for any enterprise. But at the same time, we can also use the existing privacy-preserving algorithms, even though they have some limitations. And auditing privacy risk of algorithms should be definitely part of the process of making sure that we reduce the risk of using language models on sensitive data. Thanks a lot. And if there is any time left, I'll be very happy to take more questions.
Yeah, thanks a lot, Reza, especially for hanging with us through these audio technical issues. We have a few minutes, like 2 minutes, for questions in case folks have any. Nick, go ahead.
Yeah, thank you for the presentation. I'm curious about one path I don't think is in your future list here, about deleting data. Privacy is often also about control of data. If my data was out there, but I don't want it to be, I should be able to remove it. Do you have a sense of whether large language models or others of these models have considered the possibility of how to delete an individual's data from the model? Or is it just going to require retraining, a very, very expensive retraining?
Mm-hmm. So it's a very good question. I would say it's related to a couple of points that I mentioned here, which is use publicly intended data. So nobody owns that. This is something which is generated like books, newspapers, and so on. And use private personalization, which is that my data only is used for the model, for fine-tuning the model that I'm going to use myself, right? So if I'm using smart reply or auto completions and so on and so forth, my data is, if my data is used for it, I only have access to the fine-tuned version, that fine-tuned version. But your question in general is a very challenging. That's a very interesting and but challenging problem. In the context of smaller models with some assumptions about the let's say the loss functions, the optimization problems for training models, we can use some stochastic techniques to partially retrain the model and remove the effect of somebody's data. For example, when we talk about differential privacy itself means that my data is not fully used, right? So it's almost forgotten. A little bit of more randomness would remove the effect. But I don't know if that would work in the context of language models with the complexity of optimization problems they have. I guess we should try to reduce the user cross-contamination of private information as much as possible, such that we don't get to those situations. Yeah.
Perfect. Thanks a lot, Reza, especially for joining us so late on a Friday night. Yeah, thanks a lot. There was a lot of discussion in the chat.
Oh, I see. I didn't see the chat, but I can follow up, I guess.
Yeah, I'll also send you a link to the chat.
Sure. Thank you. Thank you very much. Thanks all.
Bye. All right. Next up, we have Arthur. Let me just share the screen. And then, Arthur, I'll hand you slides control. You should be able to control the slides now. Yeah.
Can you hear me okay?
Yes, perfect.
Great. Okay, so hey, everybody. My name is Arthur Edelstein, and today I'm going to tell you about a project I've been working on for about a year and a half called privacytests.org. It's an independent project that I published separately, but currently I'm also working as a research and privacy engineer at Brave on the Brave browser. So in this talk, I'm going to give you a little overview of what I've been working on in the past on browser privacy, and then how that led to privacytests.org, and then the high-level approach to how the project works. Then I'll give you an overview of some of the specific privacy tests and results that I've obtained. And then we can have a look also at the progress that browsers have been making in privacy, which is pretty interesting recently. And then I'll talk about what I've learned and some future work.
Arthur, we can hear you fine. Would you mind just speaking up a little bit more?
Sure. Let me get closer to the mic here.
Yeah.
Yeah, so I've been working on browser privacy since about 2014. I worked at Tor browser and then at Firefox, and then most recently at Brave. So I've just been thinking a lot about different browsers, how privacy works, how privacy is leaked on the platform. And that led to me thinking more about what can we do generally about the ecosystem. And the big problem, which everybody here knows about, is that the web is a major target of mass surveillance. There's sort of a shocking thing, which is that the web is being used by billions of people as one of their primary means of reading, writing, communicating, engaging in commerce, etc. And yet this platform is extremely leaky, and it's sharing everybody's data in an invisible way. And it's exposing essentially everybody to mass surveillance by governments and corporations. And you've probably all seen this recent headline that in the US, the spy agencies are buying commercially available data en masse as a big part of their mass surveillance capability. So it's really, this problem is both government and commercial, and it's one big issue because of this data sharing. So there's a few ways that browsers are facilitating mass surveillance. The first is simply that when you visit a website, generally browsers allow trackers that are embedded in those websites to gather your browsing history. And they do this by fairly pedestrian means often, such as using cookies or by logging your IP address. But there are many, many ways that browsers will leak data. So those are just two of the most common. And that essentially has been known for 20 years. It's kind of intentional in the sense that these issues were considered in the late 90s when cookies were first introduced. And basically the decision has been, we're going to allow this kind of data sharing and allow tracking. And it has, of course, commercial benefits, especially for advertising. So that's, we could say that's sort of the intentional component. There's also a more unintentional component, or maybe neglectful component, which is that browsers will leak a lot of data that's not necessary that can also be used to track users. This is probably not something that's designed, but just that's the way that browsers are working. And so these are two sort of categories of data that are available to websites when you visit them, and then allow you to be tracked. There's also an issue with network connections. This is, I'd say, higher on the priority list for a lot of browsers to try to encrypt network connections. But that's a big area where your ISP or anybody else eavesdropping on the network can watch your browsing. So why are browsers still leaky after all these years? My feeling about that is there's a couple of reasons. The first is opacity, which is to say that privacy leaks from web browsers are hidden, and they're highly technical and complex, which means that they're basically invisible to the public. And actually, in my experience, they're even invisible to people who are working at browser companies, because it's too complicated for anybody to keep the whole story of browser privacy in their head. There's a lot of different ways that things leak. And then the second thing, which I mentioned before, is that privacy hasn't really been a priority for web browsers. They've generally been focused on other things. And unfortunately, at the same time, most browsers will advertise themselves as protecting your privacy. There's a lot of rhetoric around that, but I think frequently it's giving a false sense of security or false sense of privacy for people, thinking they're being protected when they aren't. And again, that has to do with the fact that it's invisible to people, that this data sharing is invisible. And then finally, as we all know, some of the major web browsers are getting their revenue from top trackers. They're not getting their revenue from users in general. So that's a very strong incentive to keep tracking going. So I was trying to look for, what's a way that we could try to push back a little bit on this situation. These forces are very, very huge. So, I'm fully aware that there's no simple answer to that. But at least part of the issue, because there's so much opacity in privacy leaks, is that we need to try to make the way that web browsers are leaking data, try to make that visible to the public, with the hope that that would try to apply some force in the opposite direction. So the idea of privacy tests is to bring these things to light, first by detecting privacy leaks, monitoring those leaks over time, and then getting the results, informing the public of those results, and also informing browser developers so that they're aware of what their browsers are leaking. And finally, if we can use some, we can induce some competition between browsers over privacy when that didn't really exist before, except in the realm of marketing. So I originally proposed the project at Tor in 2018. It didn't really get off the ground, but I started putting it together. And then in 2021, after I left Firefox, I started working on the project independently full-time, and I launched in mid-October. And then I also introduced tests. After doing tests on desktop browsers, I then introduced tests for Android and iOS. And so I'm continuing to work on the project as kind of a side project, and it's still a work in progress. So I'm continuing to try to add new tests and new browsers. And that's a picture of what the website looks like. You can check it out. So there are a number of challenges in trying to get something like this to work. And so this sort of lists some of the things that I was thinking about when I tried to design privacy tests. And again, it was kind of an iterative design. The first thing is just that browser privacy leaks are unknowable to most people. So what I wanted to do is just do something that is objective, and that's simply revealing the facts about browsers. And it's not really about trying to bring my opinion into the story. the second challenge is that, I could test browsers once, but they're actually updating every month. And I would like that to be something that people are aware of as things change. So what I've tried to do is publish the results every week. And then I wanted the test results to be actionable for users, which means that it's not so much about testing what your browser is doing right now, and more about comparing different browsers side by side, so that if you're a user, you can say, oh, I'd like to use a different browser because this other browser is more private, so I'm going to download this one. And then another big problem is that privacy leaks are too technical for most people. So so basically what I decided to do was to simplify the results as much as possible by bucketing results into either pass or fail. So that hides a lot of information, but that's very important because most users are not going to be interested in the technical details, and they need to just get an idea of is browser X making, allowing a large number of leaks or not. And so basically, yeah, by simplifying to pass fail, I then have a way that people can drill down if they're really interested in the details. But most people are just looking at the simple table of pass fail scores. Another problem that I ran into is that it's hard for readers to know who to trust, which is a general problem online today. That there's all kinds of fake news, false information. So there isn't really any way for me to absolutely prove that what I'm saying is correct. So instead, I've just made the tests open source, and I stick only to facts so that people can try to come to their own conclusions rather than me claiming that I have the right answer of which browser you should use or something like that. And then the other challenge that I was facing is that it's a really daunting problem because there's a large number of browsers out there and hundreds of different privacy leaks. And so my solution was just to launch early without really being finished. And then I've continued to try to add more browsers and tests as I've been able to. But it remains a work in progress. So the basic idea is that I test browsers on real devices. I have a Mac that I use to test the desktop browsers. I do that because Safari is only available on Mac. And then what I have set up is a server that serves pages that run sort of simulations of tracking, attempting to see if they can share data between two websites, for example. So I can just tell a browser, go to this page, it visits the site, it records the results, sends them back to the server, and then the server can return that back to the control program on the Mac. And it's very similar on mobile, except that I'm using the Appium library to control which pages that the web browsers visit. So there's a simple kind of data flow, which is I set up a config file that determines which browsers I'm going to test in which modes. The results come back in JSON. I then have another stage which renders the results into web pages. Then it automatically publishes them. And finally, I share the results on social media, primarily Twitter and Mastodon, to try to get public engagement. And so this is the data flow I run each week. So this is what I described before. I basically run tests on a Mac and then on an Android phone and an iOS phone. I run the tests in regular windows and also in private windows. And I also, on desktop, I run the tests on some nightly builds of browsers so that we can get rapid results on the latest changes in browsers. So there's a variety of different kinds of privacy leaks that I'm testing for. This is kind of the full list, but I'll go through some of these shortly. So the first one, I guess I'm missing a slide. The first one is state partitioning. And that refers to basically the problem that browsers tend to leak state between different websites. So if you visit website a.com and a.com has a third-party tracker embedded in it that stores a cookie, then when you go to site b.com, the third-party tracker can read back that cookie. And if that cookie is storing a user identifier, then it can track you from site A to site B. So it knows this is the same person who did these 2 site visits. So cookies are the classic example of that. But it turns out there are many forms of state that have been able to share data between sites in a very similar way. So they act as though they are cookies. And that means that any one of these individual leaks that's listed in this table is enough to uniquely track users between sites. So ideally, you'd like to be able to partition websites so this data is not shareable, this state is not shareable between the 2 sites. And it turns out that a number of browsers have already done that. So you can see in the test results here that Brave, Movad, and Tor browser have completely partitioned all of these kinds of state. And Firefox, LibreWolf, and Safari are very close. There's just one case, the blob URL API that hasn't been partitioned yet. So a lot of progress has been made here. Most recently, Chrome has partitioned some of the network connections, and I believe that they're going to be, or may have started some tests in rolling out partitioning of most of the other items here. The second one I wanted to talk about is IP address tracking, which everybody's aware of. It turns out to be a super important and difficult problem. It's been shown that users are retaining their IP address for quite a long time in a large number of cases, probably the majority of users. So that's a test that I do just to see, do any browsers hide your IP address, your server reflexive address? Only Tor browser does that by default. But it would be interesting to see if more browsers can do that in the future. Another big area is HTTPS usage. I do a variety of different tests on this. So if you look, there's been the kind of traditional idea of blocking active mixed content. That's the last row, and you can see that all browsers are doing that. The most stringent test here is the one at the top, which is looking to see, does a browser connect to an insecure website at all? And there are a couple of browsers which, I don't have them labeled here, but Tor browser and I believe LibreWolf both block insecure websites by default. So the user has to click through before they can connect to a site that's using HTTP only. Another area that I've been testing is fingerprinting. This is kind of a limited set of tests, but I think it's a really interesting area that will come after the state partitioning work is finished. So I'd like to expand this, but the basic idea is with fingerprinting, devices are leaking. Devices have a lot of unique data, and browsers are leaking that data about your device. And so that allows you to be tracked. But it's probably harder to track users through fingerprinting because you need a lot of different pieces of fingerprint, and sometimes those values will change over time. But these are just a few examples that I'm currently testing that are leaking your screen size and the position of the window on your screen and the fonts that are installed on your device. And so some browsers have successfully been able to hide this. And so I think this is showing that it should be possible for all browsers to do this. Another area that's super important is tracking query parameters. These appear in URLs when you click from one website to another. This is just an example of an ID from Google. And if you look at the results, basically some browsers are doing this. They have a list of query parameters that they block. And I think this list is getting shared around because everybody's blocking basically the same lists of query parameters, or they're not blocking any. So I think this is a pretty big distinction between browsers in terms of privacy. The next area is about trackers. I borrowed a list of the top 20 or so trackers from whotracks.me, and I just test to see whether browsers are blocking these third-party scripts. So on the right, this shows that only a few browsers are actually doing this. This is because they have an ad blocker built in. And on the left, there are more browsers that are also blocking tracking cookies. These are third-party tracking cookies. Edge is an interesting case where it has a list of trackers that it's blocking that is more limited than some of the other browsers. So you can see that some of the cookies are getting through, but others aren't. And actually, in Edge private mode, which isn't shown here, there's the same list. So actually, Edge seems to have the worst protection against third-party tracking cookies compared to Chrome, which is blocking all third-party cookies in incognito windows. And finally, the most recent set of tests that I introduced are testing cross-session tracking. So this is rather similar to the state partitioning tests that I showed at the beginning, but instead of testing between two different websites, it's testing to see if your browser retains state between two sessions of the browser. So let's say you visit a.com and then you close your browser and then you open the browser again. Is a.com able to re-identify you by storing a cookie or storing something else, let's say in the cache or in local storage, something like that? And it's really interesting. I didn't realize this, but browsers are doing almost perfectly in private browsing mode. So they really are deleting everything in caches as we would expect. So that's good to see. But I think that it would actually be really valuable to have the same behavior in normal windows. An exception would be if I've logged into a website, maybe I want that login state to be remembered when I come back. But in general, I think for short visits with websites where I don't interact with the website much, let's say I just read a page or two, there's no reason why that site should be allowed to save data about me or an identifier that tracks me the next time I visit. Yeah, so that's kind of an overview of the different kinds of tests that I've been running. Since I launched in 2021, there have been a lot of really interesting improvements in browser privacy that I've been able to watch happen in near real time, let's say. So in December of 2021, Brave partitioned network state, which meant that it was then passing all of the state partitioning tests, or nearly all of them. And then you may remember in June of 2022, there was a little scandal around DuckDuckGo and Bing trackers. So the mobile browsers started blocking Bing trackers at that point, and you could see that change. Also in 2022, Tor browser introduced HTTPS only mode by default, which is really important for using the Tor network. And then in fall of 2022, Firefox shipped total cookie protection by default, which meant that it was now passing virtually all of the partitioning tests. And then in the spring of this year, Chrome has rolled out the network state partitioning by default, which is part of that state partitioning list of tests. And what was very interesting was also just to see how that then propagated to all the other Chromium-based browsers. So it shows how important what's happening in Chromium is, that it is now the network state is now being partitioned in all desktop browsers and nearly all mobile browsers at this point.
Arthur, just a time check for maybe around 5 minutes, including questions.
Okay, I'll try to wrap up here. Yeah, and then yeah, there've been a couple more developments. What's very interesting is Safari is now announced they'll be blocking tracking query parameters in the next version. So just summing up what I've learned, all three browser engines have now been hardened for privacy in some web browsers and are passing most of the tests. And that's changed since I started. So I think that shows that there's really no excuse that every browser should be protecting user privacy, and there's no technical reason why they can't do that. And I've also it's been very actually pleasant talking to different browser engineering teams, and what I found is that basically everybody, or almost everybody, at least at the engineering level, really wants to fix these things and is very interested in trying to improve the situation. And also, it's been really fun talking to users on Twitter and Mastodon, because there's actually a lot of people who are super interested and really care about this stuff, whether they're technical or not. So there's a lot more tests that I'd like to be building and adding more browsers, but it's gonna take me years because it's a big project. Yeah, so I'd be very happy to take any questions if there's time.
Thanks a lot, Arthur. We have a few questions already. Go ahead, Tommy.
Thank you. Tommy Polly, Apple. So thank you for sharing this, and thank you for doing all the work on this. It's a great resource. Just a couple comments. One, early on in this deck, you're talking about the reasons that browsers aren't doing all the privacy things.
Yep.
And one, I think that would be very notable to add to that list, particularly for the case of protecting from network tracking or also protecting IP address tracking, all the other things, is cost. Because the cost of doing all that is very huge. And that is one of the main hurdles that collectively the ecosystem needs to be able to figure out in order to improve this.
Yeah, that's a great point.
Yeah, so it's not for lack of desire there.
True, yep.
And then just another comment for one of your earlier slides, we're talking about IP protections. There's like a label there for being Tor enabled. That's a very particular approach to it, which I get that the Tor browser is the one that does Tor. But if we were having stuff like that, I think it would be very interesting to include more things like what's going on with mask proxies and multi-hop proxies. This is something Safari's been doing for all trackers of proxying all that traffic. And for private browsing, that is now included by default for all unencrypted traffic, and we're doing oblivious DNS for all private browsing traffic. So some of those aspects, I think, will also, I very much hope to see them in other browsers too. So including other techniques like that in the table would be useful, because they are making a difference for tracking as well.
Thanks. Yeah, I totally agree. That's a great point. Hey, Matt.
Matt Finkel, Apple. Arthur, great job. And this really has been helpful in a lot of conversations, both for Safari and I know also for Chrome and a lot of other browsers. For the cross-session tests, I think we need to have a conversation about what a session means, because it sounds like you would like a session to mean when the browser is open, and then once it's closed, that session is over. But cookies persist within across, that lifetime is generally a session. So we should probably decide what we want to do about that. Also, have you had any conversations with any of the standards organizations about moving some of these tests into that purview, like what WG, web platform tests, anything like that?
I haven't at this point. I would definitely be open to that idea. I've sort of, focused mainly on just trying to stand the tests up, but I would be happy to discuss that. And yeah, I'm open to different ideas around cross-session and how to define a session, for sure.
Go ahead, Nick.
Hi, thank you for presenting this and for doing all this work. I do think it's very useful. And part of my question was going to be what Matthew just asked. So great. The other sort of comment I had was, it seems to me like many of these APIs are or functionalities are being used by websites, which causes privacy loss, and that maintaining functionality actually seems like the biggest barrier or the biggest reason that browsers are providing this functionality. You didn't include functionality in your list of reasons why browsers might not be making enough progress here. Obviously, that's something I want us to work on at W3C, is to make it clear which functionality is being used and which is being abused, so that it is easier to block abuse. But I was curious if you thought about that, or if there's a reason you're not including functionality in that reasoning.
Yeah, you're completely right. I guess my sense is that we're still kind of at the low-hanging fruit where there's a lot of things that can be fixed without really compromising web compat or compromising functionality. But you're right that there are such things, and I think, you know, my goal would be to find some ambitious but realistic point where we can say that, you know, the browser should limit what it's leaking. But, you know, for example, in terms of state partitioning, there's a huge list of things there, but they're all partitionable as far as I can see, and some browsers are doing that now. So I think we don't want to overemphasize web compatibility or functionality, because I think sometimes it can be kind of an easy out, whereas I think we should be trying really hard to make sure that things aren't leaking, and probably to the point where it's a little bit painful.
Thanks a lot, Arthur. We do have to move on. Sorry, Ayub, the queue was closed. Yeah, thanks a lot, Arthur. Again, there's a lot of discussion happening in the chat.
Okay, great.
Yeah,
I'll
thanks
take a
to you
look.
as well for joining us late on a Friday evening.
Thanks.
Yeah, Ivan, will you be presenting first?
Hello. Can you hear me?
Yes, we can. Let me share.
Okay. Okay. So since we are both Fernando and I remote, I would ask someone, the chair, to pass the slides to minimize risk of things falling apart in the middle of the presentation. We haven't rehearsed this either.
Yeah,
So
I gave you the slides, Ivan. I think there's a lot of background
okay.
noise coming though, Fernando. I'm just gonna revoke audio for you, and then you can request it again. Okay, it's much better now. Go ahead.
So we're good. And how are we on time? Do I need to go super fast, or what's?
I guess like 18 or 20 minutes would be great.
Okay.
Yeah.
Okay, so okay, this presentation is about 3 drafts that were just published recently. I will give the intro about what is this about, and then Fernando will talk about specifically about each of them and what they contain. So it's about numeric transient numeric identifiers in IETF or protocols. So what the hell does that mean? It's a fancy name for numeric IDs in protocols, and we call them, or we define them as the data objects that can uniquely distinguish one protocol object of a given type from other protocol objects of the same type within some context. So here you have some examples: the TCP initial sequence number, or the IP ID field in an IP datagram, or the DNS query ID, or the IP interface identifier. There may be more. There are more. Fragmentation ID in the IPv6 extension header, the fragmentation header, or the connection ID in QUIC, or the reference ID in the NTP. So there's IDs everywhere that are represented as usually numbers, and are transmitted as a series of bits in the wire protocol. And these IDs usually have some interoperability requirements. Like, for example, they must not duplicate during the lifetime of the packet in the network, or a datagram in the network, or they may be, there must be unique within a network, or to identify a network interface uniquely, things like that. And sometimes when these interoperability requirements are not met, bad things happen to the protocol. But the severity of the failure is not usually very well spelled out. There may be, I don't know, a duplicate ID in certain cases may make the protocol fail and a session has to be reestablished, or in other cases it may produce a denial of service, or in other cases, like for example with a fragment ID that it's duplicated, it may insert data into an existing reassembly queue, or it may be silently discarded and nothing happens, right? But these things usually are not very clearly spelled out in protocol specs. So there's a history of problems with numeric IDs if we define numeric IDs this way. And here, and in one of the RFCs that got published, we have an historical account of problems that date probably 40 years now. Like, for example, the TCP ISN issue was first discussed in 1985, in a paper in 1985. And personally, I found the same problem in some implementation, TCP implementation, with billions of devices deployed last week. So it's something that these things, these problems, security problems and privacy problems due to numeric identifiers that are not very well defined in terms of their properties or their requirements, keep happening for 40 years, and they happen in different protocols in the implementations, but also we track down this to certain, let's say, inaccuracy or lack of clear definition in the spec, in the protocol spec itself. And it happens that when we see problems in one protocol and we fix them, those fixes and the lessons learned in those protocols don't usually travel to other protocol specs. Like we see problems in the TCP initial sequence number, and when predictable sequence numbers are generated, and we address that and we fix them and we tell implementers how they should generate their numbers. But then some other protocol in some other group gets created, and the lessons learned about that were not transferred to those other groups, so the problems keep repeating. So so this is something that we observe, and that's the motivation that that prompted us to start working on this. We kept seeing these problems happening several times, and we said, so is there something that we can do to actually try to go to the root cause of this, or at least to address this going forward with some common guidance? And that's what we tried to do. It was originally something that we started working on 2016 when we were talking about, I was talking with Fernando about some potential attack that we found in the IPv6 fragmentation mechanism. And actually, Fernando was talking to me about it and explaining that to me. And I said, oh, look, wait, this sounds like really familiar. It's like the same thing that happened with IPv4. So how come we're repeating this problem? So that's how this started. It started as a single draft that provided a sample of the problems in different protocols that try to build a taxonomy of how to categorize these problems, and then to give some guidance and advice on what to do to address them. And eventually it got separated into 3 different drafts, which Fernando will talk about now. So Fernando, it's for you to continue.
There you go. I think I cannot pass the slides myself right now, right? Okay,
yeah,
I'll say like Okay, cool. So as Ivan correctly said, so our original document, our original draft was split into 3 different pieces. 2 of them were eventually adopted by this working group, and the last of them was actually published as an AD sponsored document. So I will briefly provide an overview about each of the 3 RFCs that were recently published. First one is RFC 9414, entitled Unfortunate History of Transient Numeric Identifiers. Next slide, please.
You should have control, Fernando. I gave you the
Okay,
control.
looks like, yeah. Let's see. Oh, there you go. No, wait. Okay. Okay, so essentially what this document does, the bottom line, it was obviously part of a single document. This document tries to perform a root cause analysis, and part of that was to get like a sample of different numeric IDs. We essentially document a timeline, or including events relevant to these transient numeric identifiers, considering things such as standardization work, vulnerability advisories that were published or released, and research work. Also, we documented to the extent that is possible, like POC or tools that were exploiting these issues. And at the end of the day, when you look at the timelines, it's like super evident that essentially we were repeating the same problem over and over again. One particular example is the example that Ivan just mentioned, that of the IP identification, which happens both in IPv4 and in IPv6. So eventually, the flaw was found in IPv4 implementations. It got fixed in IPv4 implementations, but then when IPv6 was specified, essentially it was specified in the same way, and the issue also affected IPv6. So it's super easy to see, like when you examine the different timelines, that actually the lessons that we learned, or that we were supposed to learn from working on float transient numeric identifiers, were not actually really learned, or were not really leveraged to actually avoid these issues from happening again in other protocols or in new versions of the same protocol, like IPv4 and IPv6. One way to summarize, the root cause of these issues is that in a lot of cases, you have specifications that employ transient numeric identifiers, and they don't really spell out what are the interoperability properties that are required from those IDs. So in a lot of cases, you cannot really, tell, what is needed from those IDs. And obviously that makes it hard to tell whether, one algorithm is doing a good job or not, because you don't really know what you have to comply with. Another of the root causes of this is that you have specifications that recommend float algorithms. Like, for example, they specify that you should select identifiers from a global counter. Obviously, that makes the IDs predictable. But also you have cases where you have a protocol specification that doesn't recommend like a way to generate the IDs in the first place. So that leaves the implementer with the decision on what to do. And normally, an implementer is doing like 100 things. So they're not going to spend a lot of time on, picking, an algorithm for generating the IDs. And quite often it happens that they pick like the wrong algorithm, or an algorithm that complies with the interoperability, requirements, but that has like negative, security and privacy implications. And finally, there's also some cases where implementation simply failed to comply with their requirements. Like, for example, we have had like BCPs for randomizing source ports of, let's say, TCP connections, like the ephemeral ports of TCP connections, and there are still implementations that simply fail to do that. I believe that what this RFC in particular, it was like one part of the the same original document at the time. I believe that it makes it clear that it's a recurring problem that we have been hitting over and over and over again, and it provides some hints as what needs to change for implementations to stop using float transient numeric identifiers. Next slide. There you go. And The second of the documents is like more lengthy and more complex, if you wish. It's RFC 9415 on the entitled on the generation of transient numeric identifiers. We're not going to discuss all the contents, but just as an overview, it introduces a taxonomy of transient numeric identifiers, try to figure out what are the different categories for these identifiers, which there are not a lot, at least when it comes to the analysis that we did. So what we did is, analyze like a set of transient numeric identifiers, like from different layers, like IPv6 interface identifiers, IPv4 and IPv6 fragment IDs, DNS transaction IDs, and so on, and try to figure out what are the interoperability properties that are required from them, but also the failure severity. Like, okay, if you don't comply with those properties, how bad do things get? And in addition to that, what this document does is, for each of those categories that we identified, try to come up with an algorithm that is good enough for generating, those IDs, and do like, threat modeling for those algorithms. And finally, also discuss some of the common algorithms that are, employed by popular implementations to generate IDs. So obviously, we are not going to cover the algorithms. It would take like a long time, but I will just like briefly mention, the taxonomy. Essentially, we came up with like 4 different categories. Okay, so for example, for the first one, category number 1, the interoperability requirement is that of uniqueness, and the failure severity is like soft failure. So you want unique transient numeric IDs, but if for some reason there's a collision, you can quickly recover from it. So it's not a big deal. Obviously, the idea is that for category number 1, you can just use like a good random number generator, because if just by chance you get you get to reuse the same number, things are not are not bad. Like, things don't break badly. Second category, uniqueness, but hard failure, meaning you cannot just run the chances of selecting a duplicate number. Numeric IDs that fall into this category is like the fragment IDs or the, for example, TCP ephemeral ports. Then we have category number 3, which is like it has a requirement of uniqueness and stability within context. Okay, with a soft failure, if you happen to select the same ID. And the specific example is IPv6 interface identifiers. Normally, what you want, at least for stable addresses, is that the IPv6 interface ID is stable within the same network. So as long as you are in the same network prefix, the interface ID is the same, so that the resulting address is stable within that network. And finally, we have category number 4, where the requirement is of uniqueness again, but we need monotonically increasing within some context. So what you want is numbers, again, that are unique, but you want subsequent numbers that are larger than the previous number that you have selected. That doesn't mean that it's a linear function. Of course, that would be like predictable, but you want the numbers to be increasing. And that's the case, for example, with TCP initial sequence numbers and the TCP initial timestamp, which is the value that you use in the first timestamp option that you send for a connection. After we define these 4 categories, what we did in our document is propose one algorithm, or at least one algorithm, for each of these categories. And the idea is that if you are specifying a protocol and you do the analysis of what are the interoperability properties and the associated failure severity that are required for your transient numeric identifiers, and if you don't know better, you can pick one of these algorithms. Okay, so you don't throw the burden at the implementer, so to speak. So that was the second document. This third document was an IETF standards track document. Okay, because the previous 2 documents were adopted by this working group, but obviously being a research group, we cannot do standards track stuff. So this RFC 9416 is security considerations for transient numeric identifiers employed in network protocols, and is essentially an RFC that tries to introduce requirements for protocol specifications. Okay. And it boils down as follows. So what we do in this RFC is introduce requirements for any specification that uses or employs transient numeric identifiers. And what we require from them is that they must specify the interoperability requirements of the associated transient numeric IDs. So if you're writing a spec, you have to tell and you have to clearly specify what's required from those IDs. This, of course, is useful so that when you see an algorithm or somebody proposes an algorithm to generate these IDs, you can tell if they are just complying with the interoperability requirements that, that have those IDs, or whether they are, for example, overloading the IDs unnecessarily obviously with the obvious security and privacy consequences. Second requirement is that you must perform a vulnerability assessment of your transient numeric identifiers. So you are using identifiers then, or what if an attacker could, for example, predict that identifier? Are there information leakages? Could those be used for performing different kinds of attacks? So that's like a mandatory part if you have a spec that uses transient numeric identifiers. The third one is probably the obvious one. You should not employ predictable transient numeric identifiers. And this is a should not because there could be some potential case where there is an interoperability requirement for the IDs to be predictable. But all other things being equal, obviously, you should never use predictable transient numeric IDs. Fourth one is that your specification should recommend one algorithm for generating the IDs. Why? Well, because even if you specify the interoperability requirements, you shouldn't throw the burden at the implementer to just pick an algorithm for that. So recommend one algorithm. That doesn't mean that the implementer needs to follow that, but at least there's a default option that is good enough. And the final one, we state that you must follow these recommendations even when cryptographic techniques are employed. And this is because, while we were progressing these documents, some people argued like, well, if we use, say, TLS for this protocol, we don't really need to care about this. And yes, you do need to care, because if you select the IDs improperly, still a number of things could happen, such as, for example, information leakages. So again, this one is standards track, and I believe it's like a super important part of of this set of documents, because it's the one that has formal requirements for specification authors. So as conclusions about this, well, this has been like a lot of work. We work on this like 7 years. It's unbelievable in a way, but it is. We hope that this will have a concrete impact on how transient numeric identifiers are specified. At least I believe that we have provided an instrument for people such that they can point at these documents when folks are introducing flawed transient numeric IDs in their specifications. And last but not least, we'd like to send a big thank you, for all those that provided valuable feedback on these documents, and also to to these working groups chairs, Chris, Shivan, Sarah, Colin, our IRTF chair, and Paul and Roman, the security IDs, because they were critical at different stages for this document actually to move forward, particularly at the last stage where we were kind of like running out of gas. So I don't know if there are any comments or questions.
There was some discussion in the chat. Did anyone have any questions for the mic line? Nick, go ahead.
Sorry that I'm speaking up so much. Thank you for this work. I intend to point lots of people to it. I wonder if you had considered, or if it would be somewhere else to consider these threats where identifiers can be linked if they are rotated at different times. It seems like your drafts don't talk about rotation. Maybe that was at a different layer or something, but certainly at the application layer, that's a risk that we're seeing, and it's a risk that's compounded by identifiers changing at different layers in the stack, and then you change one, but you didn't change the others, and then you didn't really hide your identity.
Yeah,
so
we did cover at least part of that. Like, for example, for interface identifiers, you have the MAC address that is in the link layer, which then gets, or used to get, reused at the internet layer because it was employed for for the IPv6 interface identifiers. So what our documents say is that you shouldn't reuse identifiers across like different contexts or different layers when they are not needed.
And just to add a bit on that, that's just one example, but there's several more of that. Like also in the case of stable addresses across the networks in IPv6 or identifiers, you could track with one of the original addressing modes. You could track hosts across networks because of the same thing, and generally, to be more general. There are problems when you have an ID field in your protocol and you add semantics to it that are not needed. Like, for example, you have an ID, but you add topological information to the ID, like in an interface identifier. Or you have an ID, but you add a global counter, which implies some ordering property embedded in the ID. Or in some cases, which has happened, and this is like a real world example, you have a unique ID in your protocol identifier, but some implementer decided to add the value of a kernel pointer into the ID, right? So you start breaking the requirements. You just have very strict and few security and privacy requirements for your ID field, and by adding semantics to it or overloading the semantics of your field, you are starting to create risks that you are not aware of generally. So that's why we are trying to make this assessment and this specification more mandatory for protocol designers, so they are aware of what is needed and what is not needed.
Absolutely. The Social Security Administration in the United States has an offline case of this where we put some intelligence in there and it had many of those problems. So thank you for documenting it.
Jonathan?
Jonathan Hoyland, Cloudflare. I haven't had a chance to read the document. Do you describe what the difference between this and channel bindings is, as in the cryptographic version? You mentioned in your talk privacy properties, but do you describe that in more detail in the document?
I don't remember about talking about channel bindings in our documents off the top of my head.
No, we don't.
Yeah,
we don't
you
bindings
wrote cryptographic
specifically.
techniques. Okay.
Yeah, what
Thank
we
you.
meant about the cryptographic techniques is simply that, while this document was being progress, there were let me give you a concrete example. So there was a protocol, Quick, that was specified at the time. This is a concrete example. And they didn't have their specification of the transient numeric IDs wasn't like what you'd call crystal clear, so to speak. And the argument was that, well, we don't need to do that because we use TLS, so we don't need to care about the things. So what we meant with that comment about cryptographic techniques is that even if you use cryptographic techniques, but your protocol uses things such as, I don't know, port numbers, IDs of different sorts, you need to follow this guidance too. Just the fact that you use TLS doesn't mean that you can use predictable IDs within the protocol with no problems, because, for example, you could have IDs that are selected from a global counter, and that global counter might leak, for example, the number of sessions that protocol has established since the last time the system was bootstrapped. That's what we meant.
So just to summarize, the bottom line is that even if your protocol goes over an encrypted channel, that doesn't give you a free pass to generate IDs in whatever way you want, because there may still be problems with that.
Right.
And,
so channel bindings is how you cryptographically generate an ID that's guaranteed to be unique. It's not right. It's not about AEAD or anything. It's how you generate a guaranteed unique.
Could we take this to the chat?
Yeah, sure.
Yeah. Right. Thanks all, and thanks especially to the authors. Yeah, the chairs know it's been a long time, and thanks for your work. As the documents went through multiple iterations and splitting off into several documents. So thanks also to Paul for sponsoring document 9416. Yeah. It's our first RFCs. Cool. Mallory, do you want to come up? Did you want to request access for slides? Sure.
Hi, so I was asked to come to the privacy research group to talk about a letter that was signed by some folks in the community, and more importantly, what that letter was about and what sparked it. So there are lots and lots of things I could say about the current policy landscape, but we're just focusing on two of more than that. There are more laws, even just in France, that might be interesting for folks to learn about if you aren't already following it. But this just focuses on two that have implications for the DNS and for browsers. So next slide, please. I'm going to go over the laws first to give you a bit of context, and then I'll talk about the response. So the first law I'm going to talk about, these are both proposed, by the way. They're in various states of having been approved. And I've tried to be up to date on that. But this one is, it's called the Military Planning Law. With this, you can, I include a link if you want to download this and follow the pointer to read it yourself. It's in French, obviously. It's a larger bill that is intended to set military planning strategy for France over the course of the decade. It has made progress. It's going to be implemented rather soon. But under the first part of issues we had with it, there is some focus on cybersecurity, as one would expect in a law like this. However, that's not the problem. I think the problem is that a lot of the ways the law intends to mitigate cybersecurity threats don't in general follow best practice for cybersecurity cooperation, recognizing that it's a sort of global multi-stakeholder approach because the problem is so very pervasive. It requires a lot of different actors to cooperate. The first issue is that it would require DNS providers. Obviously, they're thinking about ISPs providing DNS lookup capability, but this unfortunately would implicate any DNS lookup provider, no matter where they're located, to block domains. And it would be the sort of the National Information Systems Security Authority that would request that block, and they could do it without a court order. It gives them the power to do that. It would also require software vendors to disclose vulnerabilities, regardless of their state in terms of patching or mitigation. So this contravenes best practice, where often vulnerability disclosure, you really have to take into consideration where the patching, like where we're at in the mitigation of the vulnerability before you disclose. You have to disclose responsibly. This does not require that consideration. The next part of the law that was raising eyebrows was that comms providers, you can take that for what it means, would also have to disclose certain kinds of internet traffic that yes, there are protections that it shouldn't be personally identifiable traffic, but upon request from ANSI, anyone that's providing communications would need to respond to a request for that kind of thing. Tommy, do you want to get a clarifying question in here? It's no problem.
This is purely clarifying. On the point of the DNS providers, kind of regardless of if they are network-based or not, is there any distinction or clarity around a resolver that is running within France versus one that is running outside?
Nope.
So
any
public resolver that sees someone that they believe is coming from France around the world would. Okay.
That is right. Yep. One of the issues. Yep. And then the last thing that is related to the fourth point is that this disclosure of internet traffic and other things, there's actually data collection tools that would need to be installed at various data centers. But that and that also would not require a court order to do that. So that sounds bleak. But it's not the end of the story. There are things I'm not touching on that are not specific to the internet that you can read about in point B, which are more the broader civil liberties cases. And I would just like to point out, just for perspective here, that this is always going to be a tension with any kind of law enforcement related or military intelligence community related bills. There's always going to be a tension between civil liberties and powers, investigatory powers like that. It's not, it happens in the US all the time. Very, very common. I'm not trying to minimize the issues here, but we feel that the technical specifications around how some of these things work have specific damage proposed for the way the internet operates, and that's why we're getting involved. Whereas one might say, well, why aren't you involved in the 1,000 other kinds of ways that that spooks and cops would maybe want to get at data, which they do all the time, and they do it through democratic processes like building laws and so on. So, I'm not up here to excuse that. I'm just trying to put it in context for folks, and also to make the case for why it's important to intervene on this one and maybe potentially not other ones. So there's another one. I have another slide. This one is more broadly just been referred to as the digital bill in France. There's a third one I mentioned that's not part of this suite of things that took me some time and my very modest French skills to understand the difference between. The digital bill, again, I've got a link for it if you want to read it yourself. This is largely around digital policy. You can think of it as if you've been following a little bit the conversation around the Digital Markets Act at the EC or EU level, and also the Digital Services Act, the EU Digital Data Governance Act. This is an attempt, this digital bill is an attempt to implement those EU laws in the French context. So many countries are going to be doing this. France is not going to be the first or the last, but I think what was interesting about this proposed implementation is it actually goes beyond what is in already the DMA and the DSA in a number of ways, also leverages some of the provisions in the military law that we just talked about on that. And so where this bill is at, it's not as far as the military bill. The military bill, I think we can think of as just like a done and dusted thing. This one is working its way through somewhat uncontroversially, actually, despite some outcry by civil liberties groups, but hasn't yet reached the same. It's not quite done. There's still maybe time to influence it. So the first couple of issues are, again, requiring DNS providers to block domains. This would be done without a court order. And additionally, for the same kinds of reasons. Again, we're also not just talking about cybersecurity here. I think that's the other thing to remember about the digital bill, is it goes potentially beyond just like making sure there's no malware and spam and stuff like that on the internet. This could be for things related to, political, like the Digital Services Act and the Digital Markets Act define those things. Also, this goes into asking browsers to block certain domains, also without a court order. And in some cases, and there wasn't a lot of documentation on this that I could find, but it also sounds like not just blocking domains, but actually the browsers would need to serve users warnings in certain cases, which I think is functionality that doesn't quite exist yet, or at least isn't being used for these kinds of content. You might get, for example, a user warning if a certificate is invalid for whatever reason, but this sort of would be user warnings delivered by the browser for other things. Again, I would point you to the non-internet specific related issues folks have with this bill, and that would be in point B, where you can click through and you can learn about the ways that this requires blocking of certain kinds of media. We'll recall that currently in the EU, but specifically this was championed a lot at the time by France, that RT and Sputnik are blocked. It's that kind of stuff. And the other thing that my organization, Center for Democracy and Technology, cares a lot about at the moment, because it's cropping up in a lot of different countries and a lot of different bills is this requirement to do age verification. Even if you just need to toggle like yes or no, is this person old enough to do whatever, not age or birth date or whatever, we have really real serious concerns with this idea that age verification is an acceptable way of bucketing user experience when accessing the internet. And then a whole slew of other sort of human rights concerns. I intentionally linked to a news piece because I think they highlight in particular a group based in France that speaks on behalf of the public interest and civil society called Le Quadrature du Net, and they are quoted there. So you can also follow them specifically if you want to hear about all their other stuff. So I will ask for the next slide.
Just
Sorry.
before we do the next
Yep,
slide,
yep.
someone in chat asked what the name of the bill is because the link is dead.
Oh, the link is dead. Oh, that's a bigger problem. I'll put the link in the chat. Actually, you know what one can do? This letter has the link to that bill in the first paragraph. And again, like I couldn't really find a better way of describing. Everybody's calling it the digital bill.
You mean the Euractiv link has the?
Oh, the Euractiv link.
No,
oh,
I mean
sorry.
like, do you mean like the blog post, which is the Euractiv link over here, or did you mean some other thing?
Which link is dead, Jonathan?
The first one.
The Euractiv link. The bill, yeah, okay, my bad. That's linked from Vince's letter. So we're getting to that point, and sorry, I'll hurry up. I didn't realize I was taking so long. So yeah, so there was a response. Again, we're trying to narrow this critique to just the parts that make sort of the internet less resilient and less inclusive. VentSurf was the pin holder on this letter, reached out to the Internet Architecture Board and other folks. Also, you'll see IESG, at least one IESG member who signed it, and folks from ISOC and others. This is the extent of the letter that was then delivered directly to, well, I don't know how directly it was delivered. It was addressed to the members of French Parliament who are considering and debating these laws. Next slide, please. It makes three overall arguments. The first is that it's quite ineffective. Unfortunately, especially on the cybercrime piece, we know that best practice in cybersecurity has been sort of collaborative, multi-stakeholder global effort over the last several decades. There's a lot of lessons learned and best practice and norm setting. Some of those provisions contravene that hard-earned advice. And then the second argument is that this is really overreach. So there's a risk that in a lot of different ways this could be exploited, right? Once you start talking about, blocking certain kinds of media sites, like who and how is that determination being made, even in a democracy like France, where laws can be made and laws can be unmade, and decisions can go before a judge or not, etc. It's still a slow-moving beast. Once you create the mechanisms to do the thing, it's very hard to keep that in check. Last argument that is made is that obviously these things are meant for France within its jurisdiction, national borders. Nothing wrong with, well, not a lot of things wrong with sovereignty, that's the status quo, but they would actually then require compliance and changes to browsers and DNS resolvers and so on that exist outside of France's jurisdiction. And so that would then essentially require all of us to somewhat participate in this version of the internet. Next slide.
We just have a tiny bit of time left, Mallory. So,
You're right.
Yeah.
I'm not going to go through all of these, but it's in the slides if you wanted to get fine-grained about it. You could also just read the letter, because this is really just a bulleted list of the arguments made in the letter. And I think if we go one more, it still impacts on the internet, and maybe another one. Ta-da! That's the letter. And I would be happy to take any questions. There's already somebody in the mic queue.
Yeah.
Cool.
Lorenzo Culli, Android. I have a question and a comment. The question is, like, I really know nothing about any of this, so please forgive me if this is like blindingly obvious. But one of the things that you said many times is blocking domains without a court order, and I don't know why that would be somehow worse or different from blocking domains with a court order. Is it, because different sets of people decide, or because, it cannot be challenged in the same ways? Or is it just because, in some countries a court order is the thing you do, and in others it's not? I have no idea. Right?
Yep, exactly. So I actually have less issue with it on the blocking side than I do with the access to traffic flows side. But nonetheless, you're precisely right. A court order is shorthand for democratic check and balance on a consequential decision. And so even within France, there wouldn't then be that check and balance. And then obviously globally, I don't get to vote in French elections. So that would still impact me nonetheless, even if there were court orders involved, right?
And the comment was, Android doesn't have a browser, right? So it's not subject to anything that applies to browsers. One comment I do have is that if the difference with the status quo, or if the additional overreach is due to requesting browsers as opposed to internet service providers to perform blocking, one point I want to make is that if you rely on blocking by internet service providers, then you cannot build any security technology that obfuscates your information from the internet service provider.
Exactly.
So I guess one way to say it is if you want end-to-end security, you have to put any sort of legal intercept or blocking at the ends. And so that is something that we need to consider, right? If the endpoints say, oh, we don't want to do any blocking or anything because we want to keep our hands clean, then I think we have to understand that the consequence is that the blocking, whatever parties are going to request or impose blocking are going to do that at other parts, which is going to prevent us from encrypting the traffic.
You are exactly right. I think that this law shows it's both. So it's not an either or, unfortunately. It requires both. And I would say that it's a +1 to your suggestion to push things to the endpoints. I would take it a step further where it's opt-in by the endpoint to decide whether or not it wants that. And I think when we're talking about malware and things like that, we've already got safe browsing. So this is done, right? But in terms of do we take safe browsing and the techniques there where it's an endpoint feature and then present some sort of opt-in to users so they also miss out on a lot of other things they might not want? That's an end user choice. I think that agency is really important. Vittorio.
So we are at time, so please be under 20 seconds.
No, there's no way I can say what I have to say in 20 seconds. So. I mean, I found the letter, I found parts of these bills pretty bad. I also found several parts of your letter pretty bad and counterproductive, but there's no time to discuss it, so.
Sorry.
Yeah, cool.
Ayub Missus from Fujitsu. We don't have that time to discuss, but I think this is a very, very interesting topic. I was not aware of this bill.
Yeah.
But it's also political debate, I would say. What's the fine line between having secure cyberspace and control and blocking?
I agree. No, it's always a tension, right? This is a really important tension. And I think another thing to note that often happens in other places that have passed similar laws is folks are dubious about the actual implementation. It gives them power. Do they use it? It's hard to know. Sometimes they don't.
I do understand the people that are voting for this. They basically don't understand 99% what's that are allowing other people. They rely on technical people. But as technical people, between us, I guess we're not.
Sorry, we really do need to wrap up there.
I think the strategy was aimed at the policymakers, not at voters and end users. It was aimed at policymakers because I think you're right. In my experience, they're trying to do the right thing. This has been told that, the experts in the room, unfortunately, are often in the intelligence community. They're from ministries that work for the government, that work on these things. So they have a perspective that you can imagine is quite, focused and narrow. We're just trying to offer, here's the internet resilient view. Here's the people who care a lot about the internet working globally. Here's our view on this. And you might actually be inadvertently doing damage. That's all we were trying to offer.
Very interesting talk. Let's have this chat.
Cool.
Thanks all. Thank you so much for compressing everything in 15 minutes. Thanks all, and see you all next time.
Thanks for sharing.
No, thank you.